Hi everyone, my name is Neha Kadam and this lecture is the second part of the last lecture in which we covered how to combine the logic gates. So let's get started. So in this lecture we are going to cover how to use the computer simulations. Next is variation in Boolean expressions. We will learn about the De Morgan's theorem and then programmable logic devices. So let's first start with computer simulation. So if you remember, like there were three methods used to describe a combinational logic circuit, which was truth table, and then we use Boolean expression or logic symbol diagrams. So here a useful computer simulation instrument called a logic converter is used, which will convert back and forth between the truth table, Boolean expressions and combinational logic diagrams. So this logic converter which you see on the screen here, this logic converter makes many of the tasks performed which were performed earlier in the last lecture in a very fast and easy and in an accurate way. So this logic converter instrument, which is basically a part of a circuit simulation software by Electronics Workbench and Multisim. So the task of the logic converter is that it converts a logic diagram. You see here, this symbol is for the logic diagram. So if you create a logic diagram, you can convert that logic diagram into a truth table. Like you can make a truth table out of the logic diagram, or you can convert from a truth table. You see here this 1 0 and 1, this is a symbol for truth table. So you can convert a truth table into a unsimplified Boolean expression. You can convert the truth table into a simplified Boolean expression. So I hope you remember like how we used to simplify using min terms and using K-map. So in that way, so this is going to provide the simplified logic expression. And then you can also convert from a logic expression, Boolean expression into a truth table, and then from a Boolean expression to a logic diagram, and Boolean expression to a NAND gates only. Okay, so let's see. So here you see on this screen is the truth table area, and this here you see are the conversion options which I have already discussed. And then here you will basically have your Boolean expression area. So we will see that in the next coming slide. And so it converts back and forth from Boolean expression, truth table and logic diagrams. So this is very useful tool. You can use it to test the circuit and play with these conversions and verify if it is working correctly or not. Now let's see. So how to begin using this? So you click number of variables. So for example, here you see 3 variables have been used, A, B and C, and that's why you see this 3 variable a different combination of binaries from starting from 0 to 7. So as I said, so ABC has been used. So in step 2 you will fill in the truth table based on these variables you have used. You can use more of the variables which you see here, but right now for this particular example we are using 3 variables. So fill in the truth table, and the next step is you have to write down the output. Okay, so your output will be visible here. So now click truth table. Now the next step would be you have to click the truth table to Boolean expression and conversion option. So you can now, after you have this, you can use these conversions and see what is happening. So based on this step 3, as it says truth table to Boolean expression, so what that would be this step, because this is a truth table and we have the truth table here, and we want to convert this truth table into a Boolean expression. So let's see how it's going to give it. So this is the this option we are going to press it, so it is going to convert into unsimplified Boolean expression. So this is the Boolean expression you will see. And then you can choose more options. So click number of variables. Again, it's the same from 0 to 7. 3 different variables have been used. Fill in the truth table, and then click truth table to simplified Boolean expression. Then we will see what is going to happen. So we click here to simplified Boolean expression, truth table to Boolean expression. So previously, if you remember, we had a long expression. So now if you use the simplified version option, then you might going to get the small expression. So let's see what we are going to get. So AB bar plus C. So for this combination of truth table, so we got A bar plus B. And if you want to verify, you can use the technique which we discussed in our previous lectures, where we we found how to first write the Boolean expression based on the outputs we have. So I hope you remember, like when we have 1, we will look for all the ones, and then based on that we will put that number. So you do that, and then you can later on reduce the expression, or you can use the k-map. With the help of that also you can reduce this expression to this, and you can verify if your expression is matching with this one or not. Now try the Boolean expression. So now what we are going to do, we are going to click here, click on the Boolean expression, and we are going to convert the Boolean expression into something different. So let's see what we are going to convert. We are going to convert it into logic diagram. So once you click on this option, first click on this option and then click on this option, then you are going to see the logic diagram. So after clicking there, you have to close the window, and then you will see the logic diagram for that particular case. So for AB bar plus C is equals to Y is converted into this AND or logic diagram by the simulation software. So it's a very easy software, easy to use, and you can see all different expressions, truth tables, and logic diagrams for your circuit design. So I would recommend to use this and try to see how it works and whether it is matching with your when you solve the problem, then match your answer with the simulated answer. Okay, so now let's see what we have next. So next is a quiz, and it is pretty straightforward. It says a circuit simulator such as electronic workbench or multisim contains a useful instrument called either a logic converter or a logic probe, used to convert back and forth from truth table to Boolean expression. So definitely it's going to be a logic converter because that's the instrument we used. So we have logic converter answer here. And next question is the logic converter instrument from electronic workbench or multisim can convert back and forth from logic diagram to Boolean expression. So is it true or false? So it is true, because we saw this conversion in our previous slide. So it is true. Now let's see variation in Boolean expression. So Boolean expression textbook style and how it is different from the keyboard style. So in textbook you will usually see the notation like this for complement. So like here you see A complement B plus C complement D, C D complement is equals to Y. So here you see that A complement and D complement has been shown with a bar over here. Okay, whereas if you see the keyboard style, here this bar has been represented with the apostrophe. So you see A apostrophe B plus C D apostrophe is equals to Y. So when you use this, so this type of like apostrophe when you use for complement, you will be doing it in a keyboard when you use the keyboard, right? So this is the difference. In keyboard, you cannot use like it's impossible to use the bar, or unless you use like special characters. So it is important to remember that these are the two different styles, and so do not get confused. If you see something like this, that means A is complemented and D is complemented for this particular example. Now here is another example. So you can see that A plus B whole bar is equals to Y. So in a keyboard style, you will represent this expression like this one, A plus B, and then whole bracket, and then apostrophe. So this will be your A plus B complement. Now here, if you remove the bracket, then it is going to be A plus B complement, which is incorrect. So make sure that you use the brackets in case if you have like whole complement for two inputs, like this, like in this case. Now let's see another example. So we have A bar dot B bar is equals to Y. So in case of keyboard style, we are going to represent like this. A apostrophe B apostrophe, which means A complement B complement is equals to Y. Now a quick quiz. The Boolean expression A B bar plus C bar D is equals to Y is written as which type of like if you use the keyboard style, then how it's going to be written? So it's going to be A B apostrophe plus C apostrophe D is equals to Y, right? So this is the answer, the same thing. And let's see next. The Boolean expression A plus B plus C bar is equals to Y is written as, so in this case, you will put a bracket and then you will use the apostrophe. Okay, so it's the same thing. So here again, so if you remove the bracket and just put the apostrophe here, then it's going to be A plus B plus C complement. So make sure that you use the bracket. Boolean expression A bar B bar C bar is equals to Y is written as dash in keyboard style. So this is going to be A apostrophe B apostrophe C apostrophe is equals to Y. So this is the answer. Now let's next see the De Morgan's theorem. So the Boolean algebra, the algebra of logic circuits, it has many laws or theorems, and De Morgan's theorems is a part of that. Like this is like very useful. So these theorems, they allow us to convert back and forth from min-term to max-term forms of Boolean expression, and they also allow us to eliminate long over bars, or you can say like long complements if you have in the Boolean expression, which covers several variables. So that can be avoided using these using the De Morgan's theorem. So let's see what is the first theorem says. So first theorem says if you have A plus B whole bar, then you can write it as is equals to A bar dot B bar. So these two are equivalent. So if you have something expression like this, so for example, if you have like C plus D whole bar, then that will be equivalent to C bar dot D bar. So this is the first theorem. And the second theorem says if you have A dot B whole bar, then that can be divided into, or that will be equivalent to A bar plus B bar. Okay. So another way of saying is that when you have A dot B complement is equals to A complement plus B complement. So this is your second theorem, and first theorem is when you have A plus B complement, it will be equivalent to A complement dot B complement. So both of these theorems used to eliminate the long over bars. So this is the overbar I'm talking about. So right now this is like a very small expression, but if you have like a long expression, so in that case, if you use these two theorems, then those long overbars can be avoided. Now let's see first theorem, a plus b is equals to a bar dot b bar, and we are going to see the equivalent logic gates for this case. So you know that this expression, this plus sign is used in OR gate, right? So we are going to use the OR gate, and then we see a whole complement, so which means we are going to use the OR gate, and then there is a NOT gate, which means we are going to use the NOR gate, right? And then in this case, if you see a dot b, so dot comes when you have like AND gate, but then you have a bar and b bar, which means a bar and b bar are going as an input to the AND gate. So let's see the logic diagram. So this is what we discussed. This is the NOR gate, which has been converted into a AND gate, and its inputs of the AND gate are inverted. Or you can say you have these are the NOTs, or you can say you can use a small NOT gates here to invert the inputs. Now the second theorem, as it says, a dot b bar is equals to a bar plus b bar. So for this is an AND gate, and then NAND gate. So that's what we have here, NAND gate, and then a bar plus b bar. Plus is for OR gate, and these are the two inputs, so inputs are inverted. Okay, so this is the logic diagram for these two theorems. Now let's see how this theorem works. So there are 4 steps which are needed to convert a max term to min term Boolean expression, or from min term to max term form. So these 4 steps which we are going to see now, they are based on De Morgan's theorem, and they are as follows. So you have a b bar, which is equals to y, and next, so change all ORs to ANDs, and all ANDs to ORs. So you have here what you have an AND gate, so you will change AND to ORs. So this AND has changed to ORs. And then next is complement each individual variable. So these are the individual variables, you have to complement them. That's the next step. Third step is complement the entire function. So you have this thing here. So now in this step you have added an long overbar to these two variables. Now after this, in the fourth step, we are going to eliminate all groups of double overbar. So this is one of the formula which you have to remember in Boolean expression, that if you have 2 bars, or if it is double complemented, then in that case you can remove the bar. So if you remove the bar, so you are going to see the final expression if you remove this bar, and this is going to be your final expression. So you can see that how this has been converted into this using these 4 steps. So that's, but you don't have to every time deal with this. You just remember this formula, like if you have a dot b whole bar is equals to y, then you can convert it into a bar plus b bar is equals to y, and the same is applied for the another formula. So another first theorem of De Morgan's theorem. So you see here how with 4 steps process using De Morgan's second theorem, we have converted a conventional NAND to alternative NAND. Okay, so now next we have is the quiz. The statement a dot b bar whole bar is equals to a bar plus b bar is De Morgan's. Is it a first theorem or a second theorem? And suggest converting from NAND to an OR situation. So this is a second theorem, because we discussed the same case in the previous slide. So second theorem. And then we have the statement a plus b whole bar is equals to a bar dot B bar is De Morgan's first theorem or second theorem. So definitely this is a first theorem. So this is a first theorem. Now next we have is the PLDs. So PLDs, these are the programmable logic devices. They have the generic name for an IC that can be programmed by the user to execute a complex logic functions. So these PLDs, they are different than integrated circuits, which consist of logic gates and have like a fixed function. So but these PLDs, they have a undefined function at the time of manufacture. So if you compare like fixed logic device such as logic gate or a multiplexer or a flip-flop like D flip-flop, SR flip-flop or JK flip-flop, which performs a given logic function that is known at the time of device manufacture. But a programmable logic device, it can be configured by the user to perform a large variety of logic functions. So let's see here, and these PLDs, they have like multiple inputs and outputs. They can be used to implement minterms, Boolean expression using AND OR logic. More complex PLDs, they have like latches. Latches are the same thing, like flip-flops. You can use and other memory devices it can be used in the PLDs. And there are many advantages of PLDs. First of all, they are inexpensive and they can be programmed by the user, very reliable. So in the school, universities, in a lot of programs, PLDs are used and they are programmed by the students. Now let's see next. So PLD is generic for a programmable logic device, but they are also known by different names, including this list which you see here. First is PAL, which is programmable array logic. Second is GAL, generic array logic. FPL, fused programmable logic. PLA, programmable logic array. You might have heard this much, this one multiple times, I believe. This is very common. And then we have like PEAL, programmable electrically erasable logic. And then FPGA, this is FPGA, and then CPLD is again very common. They are used in projects many times by students. So FPGA is a field programmable gate array, and CPLD is the complex programmable logic device. So these are the few other names of the PLDs. Now a quick quiz. So PLD is a generic name of a programmable logic device. So that's the answer, which is an IC that can solve logic problems. Second, PLDs commonly have many inputs but always have only one output. So is it true or false? So this is false, because we learned in the previous slide that PLDs, they have like multiple inputs and multiple outputs. So this is false. And then PLDs have several advantages, including they can be programmed in the local lab or schools, are very reliable and inexpensive. So is it true or false? So it is true, because PLD is commonly programmed in the local development lab and school lab or shop, and not at the manufacturer. Now last, we have various manufacturer might refer to PLDs by these acronyms like TTL, CMOS, PL, PAL, PALs, ASCII code, and all these different. So is it true or false? So if you go back to my last slide, when I covered different names of PLDs, we did not cover TTL. TTL is different. CMOS is different. ASCII, these are the codes in number system. So rest of the things, FPGA, PEAL, GL, CPL, LS, this is different. So so for this is the false. This is not correct. So this is the end of the lecture. Thank you so much for watching.